All right, sorry about that. Yeah, I was saying that this course is about the Lagrangian approach to quantum field theory. So that's what we're going to be talking about, and except a little bit at the end of quantum field theory 2, we will predominantly be concerned with Lagrangians. Any questions about the structure of the course?
Yes, by Lagrangian approach, you mean path integral approach or canonical quantization?
Um, I guess both. Yeah, both of them. They're yeah, Lagrangian, Hamiltonian. Yeah, that's all sort of all the same. This is as opposed to other approaches, for example, algebraic quantum field theory or constructive quantum field theory or conformal field theory, or the geometric approach to quantum field theory. So those are very different approaches. So this is the conventional approach, which is based on Lagrangians, actions, and Hamiltonians. Any other questions? All right. Good. So let's get started. Let me repeat. If there are any things that are unclear, if there are any questions, please ask. There's no question that's too simple or trivial. All right. If you do not ask, you are risking that, like in the future, I might start talking about things that might sound gibberish to you guys. All right. So you should definitely ask. Very likely someone else in the class has a similar question. If I can answer it, I'll be happy to, but it might well be that I cannot answer it, and we'll look into it together. All right, so what's quantum field theory good for? Quantum field theory combines special relativity and quantum mechanics. It's the only framework to do so. As we will discuss in the next lecture, special relativity and quantum mechanics could not be merged without quantum field theory. As a framework that does that, achieves that, it describes elementary particles of our universe and their interactions, and the success of that could be summarized in the construction of the standard model of particle physics, one of the most successful theories we've ever constructed. So that's one pitch for quantum field theory. Quantum field theory also describes classical and quantum critical phenomena, which is continuous phase transitions. How many of you guys know what I mean by critical phenomena? Who are there any questions? Does everyone know what critical phenomena means?
No.
Could you elaborate?
Okay, this is one of the things that I'll try to actually emphasize more this year compared to last year. When I taught this last year, I think this compared to last year, I would like to include more of this to just make that point. So usually quantum field theory is discussed in this context as a fundamental theory for special relativity, and putting quantum mechanics and special relativity together as a foundation of standard model particle physics and elementary particles of our universe. But there's a completely different way of understanding quantum field theory. It's the same framework that describes classical and quantum critical phenomena. And I would like to actually call this as a pitch where quantum field theories come from. So today we're actually going to be talking about that precisely. All right. Then the third pitch for quantum field theory is that attempts to combine general relativity, not special relativity, general relativity and quantum mechanics, called quantum gravity, have been successful when cosmological constant is negative. That's one feature of like some gravitational theories. In this case, quantum gravity is known to be quantum field theory in lower dimensions. This usually goes with the name of holography. So quantum field theory is also relevant for gravity in a different sense. So these are different reasons, motivations to study quantum field theory. as a fundamental theory of particle physics, our nature, as a theory that describes phase transitions, and also as a candidate for theories of quantum gravity. Any other questions? Any questions? All right. So what is field theory and why? This is the introduction part of this course. This introduction will have 3 lectures. Today is the first lecture. We're going to be talking about the title of it is From Classical Particles to Classical Fields, the story of statistical field theory. The next lecture, we're going to be talking about from quantum particles to quantum fields. This is what usually goes with the name of quantum field theory. I'll not be distinguishing between the two, as you will see the framework is the same. And then lecture 3 is the first example of a quantum field theory, a theory of quantum sound, otherwise known as phonons. I'll just make short pauses at the end of each of these slides in case you have any questions. So far, I'm just outlining things. All right, so now we get to the beginning of the first lecture. So today we're going to be talking about from classical particles to classical fields. Let's start simple. Let's start with the classical single particle mechanics. The degrees of freedom, DOF, I usually write them as DOF, are generalized coordinates, hopefully you recall from classical mechanics, that we are going to denote them by Qi of t, and their corresponding conjugate momenta, Pi of t. Right? In the Hamiltonian formulation of physics, classical mechanics, you have Qi and Pi's, and Hamiltonian is a function of these generalized coordinates, right? It's a smooth function. And hopefully you guys remember how classical physics was constructed. It was through the so-called Poisson bracket, and that's classical physics for a single particle. For example, if the particle lives in d spatial dimensions, there will be d of these Qi's. In the Lagrangian formulation, we trade Pi for time derivatives of Qi's. So our Lagrangians is going to be is a function of Qi's, Qi dots, and time. Often we choose it so that it does not explicitly depend on time for various reasons. Do you know why? Does anyone know why we pick it to be often pick it to be independent of time?
They like conserve energy or something.
Sorry?
I think it's like if the Lagrangian is like not explicitly dependent on time, the Hamiltonian doesn't change with time. So it's like conserving energy or something.
Conservation of energy, precisely.
Yeah.
We'll get to that. All right, as an example, which is perhaps a little bit less conventional, but it's to make the point of generalized coordinates need not be position. Think of a pendulum of length L. Here, your dynamical variables are theta, the angle, and then theta dot, right? Angular velocity, and your Lagrangian is half m L squared, theta dot squared, minus GL sine theta. This is the potential, right? So this is just a simple pendulum. Any questions? All right. So I want to contrast this with, let me put them in the same slide, with classical field theory. In classical single particle mechanics, the degrees of freedom were a bunch of generalized coordinates and their conjugate momenta, right? They're functions of time. Here, the degrees of freedom in classical field theories are functions, fields in space-time. So there are phi, I, x, say, and t. So in comparison, you see here you had only time. Here you have x and t, and the fields are phi i's. They also come with their conjugate momenta, pi I of x and t. You could talk about the Hamiltonian formulation, or you could talk about the Lagrangian formulation. In the Lagrangian formulation, in analogy with the classical mechanics case, single particle classical mechanics, the Lagrangian is going to be a function of phi I dot. But now that we have these x variables, this can depend on spatial derivative of phi I and t, right? Is that clear? Any questions?
What symbol are you using for the conjugate momentum?
Pi.
Pi? Okay, thank you.
Yeah. Sorry, my handwriting could be pretty bad. If there's something that's unclear, please ask. So from this analogy, I had a point. The point is that, as you can see in comparison, single particle classical mechanics in d spatial dimensions, r d comma 1 space time in d spatial dimensions, is equivalent to d classical fields. Here d is the number of fields in time, no space here, right? So field theory in 0 plus 1 dimensional space time, if you have d copies of the field, is equivalent to single particle in d spatial dimensions, right? It's just simply the statement that in this formulation, if you have a single particle moving in d dimensional space, I runs from 1 to d. In analogy, I running from 1 to d here, it means that you have d independent fields. And the fact that here there's only time dependence and here there's x dependence, x and time, it means that the analogy would be correct if you consider classical field theory in 0 plus 1 dimension. So if you have heard the statement that field theory in 0 plus 1 dimension is quantum mechanics, this is the content of that statement. Any questions? Is the analogy clear? This is all classical. Today, everything we say is going to be classical. All right. Now we talked about single particle classical mechanics. Now consider a theory of many classical particles. So in single particle classical mechanics, we said it's like 0 plus 1 dimensional fields. 0 plus 1, 0 means the number of spatial dimensions, and plus 1 is time. If there's something about the notation or convention I use, please ask, okay? That's unclear, please ask. So I'm going to continue in this analogy. I give the example of an oscillating pendulum, but imagine just a rotor. Rotor means like similar to pendulum, you have a unit vector and there's an angle theta, and this thing is a dynamical variable. Your dynamical variable is theta of t, right? This is a single particle. If you consider many of such single particles, you can think of them as a whole bunch of these vectors oriented in two-dimensional space, because I picked it to be two-dimensional space, right? And just as a chain, they're just sitting right next to each other. And I have to pick a Hamiltonian that describes classical Hamiltonian, that describes how these classical particles interact. From this point of view, every single one of these guys is a particle, as we just described, a classical particle. So we often think of these vectors, sometimes we call them spins, classical spins, and you could write all sorts of different Hamiltonians. A nice Hamiltonian you could write down is this, Si dot, J dot, and Ij, you could pick them to be adjacent, not adjacent. There might be geometry or there might not be geometry in your picture, but some generic bilocal interactions like this. If this is nearest neighbor, that model has a name. It's called the classical XY model. Of course, you could write this down in terms of the theta variables, in terms of cosine of theta I and theta j subtracted from each other, right? So all we did was that we took many particles, classical particles, we organized the particles on a 1D lattice chain. It doesn't mean much, it doesn't mean it's 1D lattice unless I tell you that these interactions are nearest neighbor. If I just write it generically like this, there is no meaning associated with 1D lattice. It's just some generic bilocal interaction. If the interaction is nearest neighbor in 1D, the vacuum wants to align all rotors. Is this clear so far? Any questions about this? Is it clear what I mean by many particle system? Okay, so now as you can see here, the interaction tells you that if nearest neighbor, let's imagine that the interaction is nearest neighbor, then this basically tells you that this interaction term by term wants to align adjacent wants to make adjacent sites, adjacent spins or degrees of freedom rotors parallel, right? So the vacuum would be a setup where all of these guys are aligned, either all of them are aligned, right? Now, if you look at low energy states on top of this ordered vacuum, right? It's called ordered vacuum. Then you, roughly speaking, this is cartoonish. I'm just going to describe it without solving the theory. But today I'm going to solve a simpler theory and show you how, or just sketch the proof of solution of simpler theory to make this point. But just heuristically for now, what happens is that in the low energy states of this model, if you look at the excitations on top of this vacuum, what you see is these long wave perturbations. So these spins align, almost align, next parallel to each other, but there are these long wavelength perturbations. And usually the length scale on which these perturbations go up and down is some notion like the correlation length, right? So if you go far away further than this wavelength to the left or right, the spin modes are no longer correlated. If the cutoff, if the lattice spacing is epsilon, and the correlation length over epsilon is much larger than 1, this is the limit where these perturbations are very, very long wavelength. In this limit, the number of degrees of freedom, the number of particles in one correlation length is very large. So if you squint a little bit, this looks like a continuous field, right? So field theories emerge precisely in the limit where there are correlations that are developed on many, many, many lattice sites. In these limits, field theories arise. This is the limit that I was just calling this limit is sometimes called continuum limit, and it arises naturally in the so-called critical systems. These are systems near continuous phase transition. So one definition of continuous phase, or one way of thinking about continuous phase transitions, is that correlation length blows up. These are systems where correlation length blows up. So field theories that arise this way are often called statistical field theory. But as I said, the formalism that describes this is identical to quantum field theory. There's some sort of a Wick rotation, blah, blah, blah. We're not going to be talking about that. This analogy, this simple analogy, this simple classical model I'm describing is going to appear over and over again in this course and the second part of the course, just to help us understand what is going on in simpler statistical examples. So from this point of view, what I'm advocating is the picture like this. We said that single particle classical system was field theory in 0+1 dimensions. Here, many particles, if they're near criticality on a organized on a d-dimensional lattice, gives you a statistical field theory in d+1 dimensional space-time. Any questions about this? I'm going to work out an example to establish this principle.
Yeah, Nima, I have a basic doubt about this single particle in two-dimensional spacetime.
Yeah.
Yeah, suppose I have a single particle in R 2,1 spacetime. So it should be equivalent to having two fields in R 0,1, right? So for each of the
so again, you have a single particle in single particle in what to R2
in two spatial dimensions. So R of 2,1 spacetime.
Okay, sure.
Yeah, so that should correspond to two fields in R 0,1, right?
Yes.
And for each of these fields, since I'm saying R of 0,1, so I'm a bit confused. How is the spatial dependence of these fields coming into picture?
That's what, so here's what you have, right? So your single particle has x variable and y,
Yeah.
x and y as function of time is motion. They're conjugate
Precisely.
momenta, and I already called this pi's. So think of this as one of the fields, the other one, this is another field, and these are the conjugate momenta. This is 0 plus 1 dimensional field theory.
Exactly. So yeah, that's what I want to summarize. So the fields will have only time dependence, right? In this case.
That's what I mean by 0 plus 1.
Yeah. Fine. That's what I
Yes.
wanted to clarify. Thanks. Yeah.
Yes, for sure. Any other questions? So this is very quick. I don't expect you guys to get this very right now, but we're going to be working on this. Today, I'm going to be building some intuition as why this is the case.
Could you clarify what you mean by particles near criticality?
Yeah, so there's a little bit of a long story in physics. So when you have a system that has infinite entropy, it has infinite number of particles, right? So let's say your particles are finite entropy. They have like a bunch of, like say it's just a spin or something, and you have infinite number of them. You take the thermodynamic limit, right? So you want to study the system in the thermodynamic limit. What you usually do is you usually calculate the partition function. Now, the system can undergo phase transitions. Phase transitions in physics are described by situations where the partition function blows up. You have a phase transition every time, or fancier way of saying is that partition function develops non-analyticity. So partition function blows up. Now, this is phase transitions there are two types of them. There are first order or the so-called continuous phase transitions, right? Continuous phase systems that undergo a continuous phase transition are called critical systems. These systems have the property that correlation length blows up in these systems. So this is some, I guess, I'm not sure if you guys have taken like advanced StatMech. This is usually a topic that's discussed there, but it won't be at the moment. If some of this is unfamiliar, I can give you some recommendations what to read. And it won't be terribly essential for what we're discussing, but it will be very helpful in the future to understand what is going on in quantum field theory. So if you want references, I'm more than happy to share some references. This. Did I address the question?
Yeah, thank you.
For sure. I'm actually not clear on this. Do you guys learn critical phenomena in any of the courses you have? Advanced StatMech? I'm not sure. I've never taught it here. I did teach a course on this actually a couple of years ago, but yeah.
In principle, we learned that the singularities in the as you said in the partition function.
But if something is unclear, please ask, and I'll try to actually work out an example because I knew this is going to be too quick. Any other questions at this point? Okay. So far, to summarize, the point I made is that I tried to make a fair comparison between field theory, where the degrees of freedom are functions in space-time, fields, and classical mechanics. And then we saw that classical mechanics could be related naturally to 0 plus 1 dimensional field theory, where it's just the fields are functions of time, and the functions of time are just basically, say, positions of the particle. Or if you're dealing with a many particle situation, there is a nice connection. If you are near criticality, there are these like long wavelength perturbations. Then if you squint a little bit, you could think of this as some sort of a field perturbation. But this could be made rigorous, as we're going to try to do. All right. So to make this rigorous, I'm going to start with a simple example. Again, this is all classical. We're going to try to go from the Ising model to field theory. All right. So Ising model, Ising spins or Ising spins are the single particle that we're discussing, they take two values, 0 and 1, up or down, and those are the only two options. So they are like discrete. That's why you might not be able to. It might sound unfamiliar to write down to view them as a classical system, single particle system, because they're discrete. Now, if you have many of these guys on a chain, like for example, you could have spin up, 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 down, down, up, down, blah, blah, blah. Think of this as a sequence of SIs. S1 is this spin, S2 is this spin, S3 is this spin, because they take values of zeros and ones. So this could be thought of as a Morse code, 0, 0, 0, 1, blah, 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 right? So these are the states of this classical Ising model that we're describing. And for simplicity, we're going to stick to the one-dimensional setup where these chain is just 1D and its nearest neighbor, meaning that we're going to include, oops, sorry, there's a typo here. So it's basically the interaction term is SI plus 1, JI, sum over I. We could even take it to be independent of the location, bring JI out. So it's just SI plus 1, sum over I with a minus sign. Is this familiar? Is this good so far? So the first point I'll try to make here is that it's a surprising phenomenon. It's the following thing, that as I described it, the fundamental degrees of freedom seem to be these spins. So these seem to be my particles. But as we take the continuum limit, you will see that new particles emerge. They might emerge. Actually, in this example, they will. New particles will emerge, and they will have new properties that you might not have guessed. These particles are called quasi-particles. So let's discuss that. The 1D Ising model, the ground states of it, this Hamiltonian pushes it towards the following twofold degenerate. Either all the spins are pointing up or pointing down. So it's this is called a ferromagnetic phase, right? So these are the two ground states. Is this clear actually? Or so this is a ground state. If you want to make an excitation, what are the excitations you could make on this? Well, you just flip one spin. To the left of this is all up. To the right of this is all down. And this is a quasi-particle. The energy of this is E is equal to J because you just violated one of these conditions, right? Why is it quasi-particle? Because it can just travel freely with no cost. I can take this excitation and just move it around, right? The energy doesn't change. It's just like a free particle. This excitation can move around. So it's natural to call it quasi-particle. You could have two of them, like, up, all the way up, down, up again. And now these two quasi-particles, they're non-interacting because I can move them around. However, so the energy of this is 2J. That points to the fact that it's non-interacting. However, they do something funny. If you bring them together, they could annihilate. So you see, as opposed to the original case where the number of particles was conserved, these quasi-particles that emerge in this low energy limit of this nearest neighbor system we're talking about, they can annihilate. So they can collide and annihilate. So particle number is not necessarily conserved in this model. Is that clear? These are called quasi-particles. They need not be just of this form, but hopefully this example was motivating how you could start with a system where you thought in high energy, if you thought the fundamental description of the theory was in terms of a bunch of degrees of freedom, that were a bunch of particles. However, what you see in low energies is a set of quasi-particles. From a fundamental perspective, let's say in our particle physics, we see a whole bunch of particles, right? And then we list our properties. There's no way for us to be sure that these are well, at the moment, I'm just trying to cast doubt on this. We don't know a priori whether these particles that we see, for example, protons, neutrons, whether they are actual particles or they're quasi-particles emergent in some low energy limit. Is this point clear? So the notion of particle is very blurry in field theory. Any questions?
I had a question about the Hamiltonian.
Yeah.
Since we have a negative sign there, would
Yeah.
we define J as greater than 0 for a ferromagnetic system?
Yes.
Okay.
Yes. That's why I just wanted to define positive. That's why I put the minus sign there. Any other questions? So I don't want you guys to get lost in all the material I'm presenting. So I want to constantly summarize. So what I'm trying to do is I claim that many particle classical systems in some limits, low energy limits, will result in field theories. And I'm describing in an example that these field theories that emerge might have the particles in them, but these particles are not the original, might not be the original particles that you started with. That's the principle I'm trying to establish. For example, this property that these guys can annihilate, we'll see is going to be important in quantum field theory quite a lot. The fact that the particle number is not conserved. All right. So to get our field theory out of this, what we're going to do is we're going to play this game of magnetization and coarse graining. It's called spin blocking. It was introduced by Kadanoff back in the 50s or early 60s to understand the so-called normalization group. So the idea is this. We were working with degrees of freedom that were these fundamental particles, SIs, right? Sitting at each side. So Kadanoff said, let's just say that for some reason I'm only seeing very long distance physics, and the smallest thing I can resolve includes already millions, billions, or maybe trillions of fundamental particles. This is a very realistic setup when we have Avogadro number of atoms, and in the lab we're looking at like a chunk of material and we have finite microscopes. So the smallest thing we can see in the lab might be like many, many, many particles, right? So instead, if you're working in such a limit, the relevant degrees of freedom are not the individual spins, but they're coarse-grained, they're averaged. So there's like magnetization. For example, if within one unit cell that you can resolve, you have n of these magnets, these spins, the thing that could be measurable is the average sum of these guys. This is called magnetization. So let's say there's, oh, sorry, I think I changed notation. Now, it's pretty clear that an individual spin could take either 1 or -1 as values. However, if these coarse-grained magnetization variables can take any value from -1 to 1 if there's a lot of them. So in the limit of n going to infinity, this m variable looks continuous. Now, if you think of your system as these blocks in each of which there are many, many, many large number of spins, this continuous variable that you were thinking of, this field, we're going to call it field, becomes space dependent, right? It depends on the space. Now, if you also further know from the picture I was drawing before that we're going to be interested in long wavelength perturbations, right? That this field varies slowly over this one-dimensional line, what we're going to naturally get is a field theory. So this M of X, let's say this X is this like the smallest thing you could resolve at this point, becomes a local magnetization field. Any questions at this point? We're still working out heuristics. It's the first lecture. The next lecture is also going to be very heuristics, and gradually the course is going to become more and more move towards quantum and like relativity. By the way, at this point, there's no relativity. And I'm still calling it field. Well, we will see. Any questions? All right. Now, there's actually, so here I argued for this variable becoming continuous, but there's actually a trick that can replace the unsigned single variable that was discrete, +1, -1 spin. Oh, sorry. With a continuous variable. Let's say instead of the variable s, I introduce a field phi of I, for example. Instead, I can't think of this as phi of I. I don't have to call it x. And when I was just taking my state to be up or down, I'm gonna take phi of I. Phi is a continuous variable. I'm gonna introduce a weight associated with it, which is e to minus g phi I squared minus 1 squared. If g is very large, this probability measure basically tells you that the field phi pretty much takes two values, +1 or -1. Right? So it seems like I can already, by playing some probabilistic weight, I can mimic in the limit of g very large, I can approximate a discrete variable by continuous variable. Now, is that clear actually? The advantage of this is that now if you take your nearest neighbor Ising model, which was sum over, I already called Ix, x, sx, sx plus epsilon, epsilon is the lattice cutoff, and just by hand subtract a constant term from the Hamiltonian, right? In classical physics, nothing changes. Just subtract that by hand, you could repackage that as a square of sx plus epsilon minus x squared. Now, as you take the continuum limit, this is phi of x plus epsilon. This is phi of x. In the continuum limit, this becomes 1 over epsilon del x phi squared. Sum over x becomes integral over d of x. So you obtain this del x phi squared term. Remember in comparison I was making between classical particles and fields, I said that here. I said that our Lagrangians here had qi and qi dot. Here we had phi I dot and also these derivatives. That's what we're finding, right? We're finding these terms that in the continuum limit, they look like del x of phi squared in the Hamiltonian. Is this clear? Any questions about this? Any thoughts? Have I lost you guys already? Wow, does not sound good.
I just need a clarification. How did you arrive at the last line from the spins to the fields? How did you just write the last line? I'm confused there.
This line?
Yeah. Yep, that line.
So I just replace phi s of x plus epsilon by phi of x plus epsilon. S of x is phi of x, right? So this is the structure I obtain, right? Right?
No, I mean just I understand that, but how could you just replace the individual spins with the field straight away?
That's the trick I was using, right? I introduce a set,
Yeah.
replace a discrete variable by continuous variable, and play this game. One of the things that perhaps you haven't seen so far in physics, and is perhaps a little bit shocking to you, is that if you're looking at the from the point of view of low energy physics, this degree of freedom they introduce in the UV is fictional. If I'm looking at low energy perturbations, I could reproduce the same physics if I started with SI, which was a discrete variable. The same physics will also appear if I start with a continuous variable with such weights. This is actually a very deep statement about field theory and even about quantum field theory, that by looking at low energies, infrared, there is no way to know what is in the ultraviolet, very, very large energies. As a matter of fact, there could be many, many different ways of repackaging, like there could be many, many different UV physics that gives you the same infrared physics, right? For example, we see in the universe, we see particles, the Higgs particles, nanomolar particle physics, we see electrons and protons, and this is low energy for some very, very high energy physics that we don't know. And there could be many different high energy theories with different degrees of fundamental degrees of freedom that reproduce the same low energy physics, right? This is a very important principle called relevant versus irrelevant deformations. I'm not discussing that. That's going to be part of quantum field theory too, but I'm just describing a simple example. So from the point of view of field theory, particles could be emergent, could be like you have no way of knowing whether they're fundamental or not. They could be completely emergent. These degrees of freedom that you see these are just some effective things that you see at low energies. Is that principle clear? Any other questions? Yeah, go ahead.
So like, I'm assuming that like what this is saying is that like you're integrating over some differential change in phi. Well, what does it mean when you write down like integral d phi x squared?
Well, we'll see that actually. We'll see that.
Okay.
Yeah. I'll work towards that. But this is a kinetic term in the action for our scalar field. You're familiar with Lagrangians that have phi dot squared, right? So it's not a stretch much. It doesn't take much imagination to imagine that such terms can appear, right? I have a hard time writing on iPad when I'm holding like this. We'll see explicitly that they do appear. As a matter of fact, if we wanted to push this analysis, it's just lecture one, I'm trying to motivate it. But if you were patient with me, I could do a calculation. From this, I can derive scalar field theory on the nose. This theory actually is, in the low energy, is described precisely by scalar field theory, the conventional free field theory.
Okay.
Any other questions? All right, let's make this a little bit more rigorous.
Nima, there's a question in
yes.
chat, I believe. Sorry, there's a question in
Please
chat.
ask questions. Do not type in chat because I don't see them. Yeah, what is the question?
It says that can you elaborate on how particles can be seen as an emergent property?
Well, I give an example, right? So I gave an example. Where was it? No. This one, right? This is an excitation. This is a one excitation, right? That can move freely in space. I'm going to call that a quasi-particle. It has exactly what you expect from particles. I can have one of them, I can have two of them, I can have a bunch of them. They can move around, they could interact. In this case, they don't interact unless they collide. They could collide. And what is a particle at the end of the day? This is one of the most important lessons of field theory. In field theory, what I'm trying to motivate here is that in field theory, we make a departure from particle picture. When physics is described by a bunch of particles that move in space and interact, we replace all of that with these fields in space. And then at some point in space-time, at some point in the course where we're gonna go back to this and revise this and see, well, today we're gonna say why field theory picture is more fundamental than the particle picture. Next lecture, we're gonna say that for the quantum physics, we'll see how quantum fields are more fundamental than quantum particles. And then at some point in the course, we're gonna abandon the notion of particle, and then we're gonna rediscover what a particle is using field theory. Questions? All right, let me work out this example. Maybe this will definitely help. Let's consider finite temperature. In finite temperature classical physics, what we compute is a partition function. So the partition function is a sum over all spin configurations, e to minus beta, beta is inverse temperature, h of that spin configuration. And I already told you what h is, right? H was just this functional that you plug into it, the spin configuration, and read off an energy value, right? So this is what partition function is. Hopefully this is familiar from classical physics. Now, what I'm gonna do is this. I'm gonna use a coarse graining by saying that I have to sum over, I have to sum over all field all configurations of spins, right? I'm gonna package these guys into groups, define M, as the local magnetization variable. This is an exact packaging of the same information. First, I'm gonna sum over different M configurations. Sorry, I'm gonna fix M, a particular M, and then sum over all the microstates corresponding to this macro configuration, and then sum over all M's, right? So this first sum says, fix the value of M1 here, M2 here, M3 here. Given M1, M2, M3, what are the microstates? How many different ways can I rearrange these microscopic things so that M is the same? First, I'm gonna do that, then I'm gonna sum over M. Is that clear? Just a repackaging of the sum. It's an exact repackaging of the sum.
Yeah.
Now I can just call this sum, calculate this sum, take the logarithm of it, minus 1 over beta, and define a function of M. This looks like a new Hamiltonian for my coarse grain variables. That if I plug in this Hamiltonian and sum over all so this looks like the original thing. I just redefined what my degrees of freedom were. I coarse grain my degrees of freedom. At the end of the day, it calculates the same partition function. Here I was describing it in terms of this fundamental spin degrees of freedom. Here I'm describing in terms of these coarse grain degrees of freedom. But it reproduces the same thing. The Hamiltonian of these fundamental degrees of freedom looks different from the quote-unquote Hamiltonian of this coarse grain degrees of freedom. However, it's the same, it reproduces the same physics, right? Now, in the continuum limit, so here is like, I'm drawing it as if it's higher dimensional. When there are each of these blocks that are calculate M's. So there are many, many, many excitations, this m of x becomes a continuous variable. So what I have is a sum over m of x e to the power minus beta of m of x. Now, if m of x is a continuous variable, this is a functional. So I'm summing, I'm actually integrating over all functions of space. Is that clear? So I'm just repeating what I said before. Now I'm going to coarse grain over a setup where there are many, many degrees of freedom inside this, so that these coarse grain variables I was introducing become continuous. Now I can think of these as different points in the continuous space, and this m of x becomes a function of space, right? And now I have to sum over all functions of space. That sum has a name. It's called path integral. But what we're gonna say that next. Are there any questions about what I'm doing? It's hard for me to, I don't see you guys, so it's hard for me to evaluate what is going on.
What's actually spin blocking? Like I didn't the connection.
Spin blocking is a following procedure. You had a bunch of spins, say 4 of them. You block them together as a new coarse grain variable, which is the average of these guys. You abandon, you forget about the fundamental spins. You replace them with these coarse grain degrees of freedom. You rewrite your partition function in terms of these new coarse grain degrees of freedom. You still reproduce the same physics, but you forgot about these microstates. Like, for example, a very, very concrete example is you could think of the blocking 3 spins and into one unit, and call that what was it called? The majority vote, right? So you could replace 3 degrees of freedom with 1 degree of freedom, and this we could call it majority vote. If it's up, up, down, this becomes up. If there are 2 downs here, right, it will be down.
Sorry, don't you lose some properties when doing this spin blocking?
Of course you do. Yes. What do you lose? What do you lose? The details of the microstates is what you lose. But these details of microstates might simply not be observable to you, because I motivated this saying that this is the smallest thing you could see with your microscope. Nonetheless, that smallest thing is made out of billions of fundamental particles. They just don't see them. We look around in our universe and we see a bunch of particles. The highest energies we've achieved in LHC on our experiments are a certain amount. We have no idea whether these particles we see are not made out of many, many, many other particles that we have not discovered yet, and we just haven't had enough energy to discover, right? So what we see is some sort of coarse grain description. That's the information that is just not accessible to us. Does that make sense?
Yeah.
So I imagine that you guys came to this course thinking that we're going to be talking about high energies. And now what you're seeing is the exact opposite. I'm talking about field theory emerging at very, very low energies. We're going to get there. Just be patient with me. Our fundamental understanding of field theories is that how they come about, how they emerge, is as the low energy limit of something a lot more complicated. So, for example, the field theories we see in our space-time, what is high energy or low energy? It's relative to the energy scales that you have available. We'll get there. We'll get there. The conversation so far classical. I'm trying to keep it simple. as we build up towards fancier examples, and you will see that the physics becomes closer and closer to what you expect. So as the lattice spacing becomes very small, m of x becomes a continuous function, and summing over all functions m of x becomes something that we call functional integral. So this course, we're going to discuss functional integrals in detail. I don't expect you guys to see it right away or be able to understand what it means. We're going to discuss this. A lot of the things that I'm going over is sort of like an overview of the sort of concepts that are going to appear over and over again in this course in fancy context of quantum field theory. But the point of this example is for you to see that it comes up in very simple examples, such as one-dimensional classical Ising model. Same technology, same ideas, notions appear even in this simple example. So your partition function becomes, this is just notation for now. We're gonna one day, very soon, explain what path integrals are, but this is just like an integral over all functions of space with e2 minus beta. This is some sort of an energy functional for m of x, right? You could think of this as some sort of probability measure in some sort of thermal ensemble, right? So the space of configuration is now the space of all functions m of x. In classical physics, the configuration space was all the QIs, right? Where the position of the particle is at different times. Here, the configuration space is all the functions of space. We've gone from particles to fields. Any questions?
What's the subscript on that F?
Nothing. Landau-Ginzburg. But I did not say those words. What I'm describing is this Landau-Ginzburg theory of critical phenomena, but that F usually comes with LG under it. But yeah, I did not want to introduce it. Any questions? All right. Hopefully this will not too much torture. What I wanted to do for you guys at very, very high level, using extremely simple examples, I wanted to tell you that even in classical physics, some of these concepts that are related to quantum field theory, such as path integrals and continuous functions, namely that what we call fields, appear naturally as we try to describe very like mundane physics, such as like classical Ising model at finite temperature. All right. So let me summarize. Today, what I tried to do at some high level is to just describe for you how to go from classical particles to classical fields. We saw that field theories capture the low energy physics of classical many-body systems with local interactions when they go critical. This means that the correlation length is very large, or in the terminology I use, the smallest thing you could see contains many, many, many degrees of freedom, right? So I encourage you guys to read more about this concept. I just try to argue very, motivate this heuristically, but of course, this is like a whole subfield of physics called critical phenomena, and field theories have appeared there. You could spend your whole life studying this topic. In these systems, low energy excitations, another point that we made is that the low energy excitations that emerge in the systems, they're different, could be different from high energy particles. We call them quasi-particles. For example, we saw an example where these guys could pair create and annihilate, can be pair created or annihilated. This means that the particle number for quasi-particles need not be conserved. And importantly, field theory can capture that. Field theory is an intrinsically many particle theory. This is perhaps the most important point I wanted to make today. Field theory is a formulation which is inevitable every time you have the phenomena that involves particles annihilating and creating being pair created out of nothing, or just due to some energy fluctuations, or annihilating. Every time you have that, the particle number conservation is no longer valid. So the particle picture falls apart because particle picture starts with a bunch of QIs, right? That's just your description. And whatever dynamics you write, the QIs are QIs. The numbers cannot get larger or smaller. Classical physics of particles does not allow for fluctuation in the numbers. If you want to describe physics as a just motivated, where the particle number is not conserved, field theory is the natural language. Is that the first summary? Are there any questions? Because I'm going to change gears. This lecture one, this is a lot of heuristics, but I didn't want to start by writing the Klein-Gordon equation trying to quantize it. I wanted to relate it to very simple physics that you already know, hoping that you would take these simple examples and think about them a little bit more to see how, think a little bit more about them. Questions? All right. Now let's switch gears. I want to tell you a little bit about what is this thing, this classical field theory, that we're going to spend half of the course studying. And the quantum field theory is going to be an analog of this, just a little bit more complicated, but many of the phenomena is already visible at the classical level. I want to name 3 principles: locality, symmetry, positivity of energy. We're going to see, actually, this is going to be a big part of the course. Locality has aspects that's locality in space, locality in time. Locality in space is going to be related to the action principle, the fact that we use Lagrangian densities. Locality in time is going to be related to causality and stability. Symmetry is going to be related to conservation laws. And positivity of energy is also related to stability of causality. So these 3 things will appear, this whole semester, these words will appear over and over again, in context of classical field theory and quantum field theory. These are the 3 principles that I want you to have in mind. We're gonna discuss them in details, both in classical field theory and quantum field theory. If there are any principles to field theory, these are the principles: locality, symmetry, positivity of energy. I cannot stress this enough. Now, exactly because of that, part 1 of the course is going to have the following structure. In section 2, we're going to discuss locality. We're going to discuss action principles, dynamics of the fields, how to derive the equations of motion. We're going to discuss symmetry in section 3, which is conservation laws, Noether theorem, and its consequences. Section 4 is going to be relativistic field theory. This is when we start talking about relativity. That's where, as a particular type of symmetry, these are space-time symmetries. And then in section 5, we're going to be talking about gauge theories. These are theories that have generalized symmetries. That's one perspective. The other perspective is that they have some non-local observables. So this is going to be the first part of the course, and we're going to go over these principles. Positivity of energy will sneak in here and there. I have not turned it into a full section. All right, any questions? So this is the end of this lecture. It was mostly an overview lecture and just setting up which direction we're going to be going. So to repeat that, part 1 of this QFT1 is going to be a classical field theory, and it will include these sections. We're going to discuss locality, symmetry, relativistic field theories, and gauge theories. Gauge theory is theories that could be understood as generalized symmetries, and theories with non-local observables. Any questions? All right. So that was, oops. What happened? Yeah. Sorry about that. Okay, so that was lecture 1. As I said, unfortunately, the first few lectures, 4 lectures, is going to be on Zoom, so it will be like this, but we'll try to use Chalkboard. Another thing is to say is that the first few lectures, of course, because we're setting the stage and outline of the course, it might sound very heuristics, but of course, quantum field theory is a course that's all about calculations. So we're going to be doing a lot of calculations. All right, any questions, any comments? How many of you guys had seen critical, did anything similar to this, like statistical field theory? Okay. Yeah, it is really our modern understanding of quantum field theory is statistical field theory. This is like really how we think about it nowadays. But of course, quantum field theory has gone through many decades of work and studies. Any questions? We're good. How many of you guys are condensed matter theorists now? Let me just, okay, that's hard to count. All right. If you do want a topic that you would like to particularly to be included in the course, as I said, I could arrange for that. Just send me an email. Send me an email because I could take the course in various directions. I'm a high energy theorist, so it's easy for me to jump into quantum field theory and S matrices and ignore everything that has to do with phase transitions. Or I could describe the same physics, never saying S matrices and just talking phase transitions. All right. Thank you so much, guys. I'll see you on Thursday.
Thank you. Bye.
Thank you.
Thank you.
Thank you.